definitely great to have also one of our key partners of the project here. And Bruno will be sharing some of his expertise, which goes back also, I think, about 2 decades now, 3 decades, more or less, 4 decades?
Between 2 and 3.
Between 2 and 3. Okay, so and also with a vast experience now of having done lots of research and interesting insights. So Bruno, the floor is yours.
All right, thank you, Ulrich. I'll be talking a bit about, and it's been mentioned already, cloud nativeness. What does this entail? But first, I'll go back in time a little bit to just show you how did we get here. And I'll focus on how applications are built. And I think looking at the average age here, you'll probably know where I'm getting it from. We used to build applications in monoliths. We still do, I recognize that, but this used to be the only thing that you could do, building it in monoliths. And you have your users and then you have your application. And these applications started growing more complex. So they started building layers into that. And you had like a presentation layer, a persistence layer, then your business logic was a separate layer, and then some shared services and dependencies. And they all fed data from one or typically one big data source, think your SQL server or so on. This was perfectly fine. But once the application started growing more and more, so the complexity of the application started growing, they started seeing like, okay, this is starting to become quite unmanageable in terms of flexibility, in terms of leanness, in terms of coding. We should start focusing on cross-cutting flows. And cross-cutting flows, you would see like, okay, we have everything to do with users, everything to do with products throughout these separate layers. So they're introducing a kind of separation within that monolith, and specific teams could be working on those cross-cutting flows. Now, this is actually not the best way of working if your application is very complex. Why? Because if this is one executable, let's say, then it becomes quite complex to get new features in there and to get them stable in there. Because you could be introducing a bug in one of the other layers, or you could be in need of a library which causes problem for the other code in there. So that's what it says here. You could introduce unwanted side effects and bugs once you start adding extra things. And this is, of course, problematic if you're going for this lean, mean productization of your software. There's another problem. If you need to scale, you can do that in 2 ways. Now, I think you know vertical scaling. Vertical scaling is basically, I'm going to put it on a bigger server. I'm going to put more RAM into it. I'm going to put more storage into it, bigger and faster CPU. This works, but only so far. You can only scale so far in terms of one single machine. So this is not really a solution. So the other way of scaling your application, if you're seeing a lot of traffic, is let's do it horizontally. Horizontally means we're going to take that big executable, that monolith, and we're going to be separating it or sharing it over a number of different machines. You see that here, so you have 4 different machines, and in front of those 4 machines, you put a load balancer. Load balancer, which basically acts as your single point of entry towards your application, and which shares your load among these different application stacks. Now, the issue is still there. If your application grows, you still need that full application stack on a single node. Let's say this would be Facebook, this would no longer be feasible. If this would be Netflix, this is no longer feasible. Why? Because the application has grown too big for one server to handle. So they started thinking like, yeah, but maybe we should only host a number of these cross-cutting flows. That would certainly alleviate our problems, will it not? Well, the answer is no, because you still need all the technologies in those stacks. You need your presentation technologies, you need your persistent technologies, you need all the layers there, even though you're only addressing a few cross-cutting concerns in your application stack. So still issues with scalability, still issues with load balancing, and this is what's mentioned here. When you deploy, you need your full application stack on each server. This is no longer feasible for these larger applications, let's say. Also, in terms of fault tolerance, if something goes wrong anywhere in that program, your full application typically crashes. that's not really the intended way of working. And in terms of dependencies, say that you want a certain library, you as a team, you want to use a certain newer library than what the other teams are using in there, you might end up with issues. Also security, you've just programmed something new in the mobile flow. This opens up a security hole towards the persistence of the other flows. Well, you're in a bit of a trouble there. So in terms of security, also the fact that everything is contained in one monolithic application stack is not the greatest, especially when you go to these, and keep that in mind, to these larger applications. So income services, we've heard it mentioned before, services which separate our application into a number of individual units. The typical definition is that they're independently deployable, they should be replaceable, they should be upgradable without impacting the other services. It can take many forms, can be serverless cloud function, that's already quite advanced, but typically it's just a web app running in a container. You have an API. This is important because it's the API that defines what your service can do. It also defines how you can communicate between your different services. So all the operations that you can do between your services. So they said, okay, service-oriented architectures for the win. We'll just separate our application, our monolith, into services, and the case is closed. So what they did at first, when service-oriented architectures was lauded, we're going to have this big user interface service, and then we're going to have a big business logic service, and we're going to separate them so we can deploy them on separate machines, and we'll have a big persistence service. And this worked up to a certain level, because as your applications grow, this particular service, this was just a monolith in itself. So your business logic as one service is basically not a good option. You can see also here that still there was typically this large, let's say, Oracle database or SQL database, which delivered the data to the applications. This is how you could see a lot of applications being deployed, I would say, 15 years ago. Okay, so applications kept growing, complexity kept increasing, and there was this need for more agile development, more agile delivery of applications. So this really doesn't allow you to do that because the services are too big. So they said, okay, but why don't we make these really small services, small microservices? It's also been mentioned a few times here. And let's not think in terms of these persistence and presentation and business logic layers. No, let's think about business logic. Yeah. Particular business logic forms one microservice. And you can see an example here. You have a billing service, you have a service dealing with everything to do with users, a service, everything to do with your configuration, everything to do with your products. This is probably already a too big microservice, by the way. Everything to do with your shopping cart, with your recommendations, least, most viewed lists, and so on. So you have a lot of these services which focus on one particular aspect, and they do it well, or they should do it well. One other thing that you notice here in the figure, and I'm going to ask it to you, what do you see different here? That wasn't there in the previous slides. Yeah. Yeah, you see that there's suddenly a lot more data sources. Well, that's also a typical aspect of microservices. No longer do you have one source of truth for your data. No, now every microservice can actually choose their own technology or their own data store technology for storing their data, which means these become leaner, more flexible, and technology-wise, you get to pick. One thing that's also quite different is that you now see a lot more communication, which means you will need to have a lightweight communication protocol in there. Gone are the days of these enterprise service buses where they said, oh, we're going to put an enterprise service bus and then we're going to do manipulations between the communication between these services, and we're going to do all kinds of fancy things like adding parameters and translating between APIs. That's not what you want to do. You want it to be as lightweight as possible. Lightweight, things like REST, JSON messages being exchanged, and so on. So what's the definition of microservice architecture? It's basically an evolution of service-oriented architecture, where they said we're going to be developing a single application as a suite of independently deployable services. Each service runs in its own process, is independently replaceable, so you can upgrade it whenever you want, and it communicates with lightweight mechanisms, HTTP, TCP, MQTT, REST-based protocol, and so on. They're built around business capabilities, so not around technical capabilities like persistence or certain aspects of business logic. They should always be fully automated deployable. What does that mean? Well, I'm going to go back one. Let's say that your application is now divided into 50 microservices. This is not an exaggerated number. We have applications that are consisting of 50 microservices. You don't want to manually deploy these each time you have a new version. You need to have some form of automated deployment machinery set in place. Because if you do that a lot, we're developing lean, you don't want to have manual errors in there. So automated CI/CD pipelines. You don't want centralized management. You don't want someone orchestrating all that. Yeah, you don't want someone saying, oh, service A, now you should talk to service B. And service B, your answer should be delivered to service C. They need to find each other. They need to be able to talk to each other. They need to know each other's APIs. Very important, they can be written in different programming language or using different technology stacks. I think if you want to be lean and someone tells my team, okay, we need something very statistical, I'm going to tell the people that are working on that, like, maybe you should look at R, yeah? The R programming language. It will already alleviate some of the things that we need to do statistically wise. If someone needs to do something very quick and dirty, well, let's say quick only, AI-based, I'll probably tell them, look what's available in Python. Yeah. Gone are the days where you go to a company and you say, okay, but our application, it's C. You have no choice, it's C, okay? You need to build a web application in C. I would say, no, thank you. Yeah. So different programming languages. Use the thing that shines for what you need to do. And of course, be a bit mindful. Don't go using something completely exotic that no one knows about. Use different data storage technologies. It's not all SQL. Yeah? If you need to store time series data, use a time series database or a search engine. If you need to store relational data, use a relational database. If you need to store documents, use MongoDB or something else like that. So there's a lot of different storage technologies. Okay, I won't go into the recommendation to use a MongoDB. There's a lot of different data storage technologies that you can use. We have an application, for instance, that is storing IoT data. If we would have stuck with relational data stores, we would not have reached the performance that we're getting now, where we can absorb hundreds of thousands of events per second. Why is that? Because we're using time series data stores that are optimized for time series data. So here, again, you have a choice. Now, in terms of adopters, there's a lot of companies adopting microservices. It's not a holy grail, by the way. Don't transform everything into a microservice. Some things are perfectly fine staying as a monolith. But if you have a very rapidly growing application and that needs to be very scalable, then microservice-based architecture is probably a good way of approaching that. And you see a lot of the names here, a lot of the companies that also grew quite fast, like Uber, Spotify, Zalando, that have applications scaling quite massively. Netflix, for instance, is quite a strong microservice proponent. Yeah, true. Yeah, I wouldn't say, like, you gave an example of microservices where you said 200 microservices and there were 5 developers. Yeah, but that's, for instance, for my team also the case. We have a production application called Obelisk that has now been running for 5 years in production, which has 50 to 60 microservices. I have 3 developers for that. I dare say we would not have been able to do Obelisk if we would not have approached it through a microservice-based architectural style, even though technically we don't have the teams for it. And that's basically because I don't have the people for having separate teams. You're completely right. All these these are not your startups. These are big companies with large engineering teams. So microservice, for us, it's a way of loose coupling. It's a loosely coupled application design, let's say it like that. So think of this. You have this application, you have 50, 60 microservices. Each of those microservices has 1 to 100 instances, depending on the load. So how do we enable that? How do we deploy that in our data center? Well, you might think, okay, so let's use virtual machines. It's a proven technology, virtual machines, it works. And you would have your service code. Yeah, pointing doesn't work on a tally. You have your service code, you have a VM image builder, spits out a VM, and then you deploy it in whatever cloud you choose or in your own data center. This works, but it has some limitations. It gives you encapsulation, gives you isolation, but it also gives you not that efficient resource utilization. Why? The VM is quite sluggish when you compare it to a container. It has its own operating system which needs to boot. It has emulated hardware instead of direct access to your hardware. I know purists will probably correct me in that, but relatively slow deployments, think minutes. If you need to scale very rapidly, let's think that in the case you want to build a ticketing system, you're selling the tickets for the newest Coldplay concert. I wouldn't want to build a ticketing system on VMs that need to boot up, yeah, because it will not work. You need something very agile, very fast booting. You need something that can scale very rapidly. VMs here are not the best fit for that. So in come containers, and we've already talked about containers. The main difference that you'll see between VMs on the left-hand side and containers on the right-hand side is that VMs have an operating system and kernel inside them, yeah, which need to boot when you boot the VM. Containers, they typically can directly go to the host operating system and kernel. There are some intermediate technologies here, but I won't delve into those. This here means you can have direct hardware access. Yeah? You can still have isolation, but on an application level thing. Here you have hardware-based isolation on your VM. So you have more security than in your containers, but in your containers, you have better performance. So that brings us back to the microservice-based story. Why don't we do that in containers? So we have our service code, we pass that through a container building tool, we end up with container images, and we spread these container images out over our data center, our cloud. One thing you'll notice is, wait, didn't you just say you wanted containers? Why is there a VM here? Well, a lot of times, these are actually deployed on running VMs, VMs that no longer need to boot, but that are already running. For us, for instance, in our data center, a lot of times for reliability, it's actually we're running it on vSphere, yeah, on VMware vSphere, just to have a reliable substrate underneath. So containers, which boot up in, let's say, 1-2 seconds, depending on, of course, if they're available locally or if they're very large. And I think the most popular container engine, everyone will probably have heard of Docker, is Docker. Was conceived in 2013 because they noticed, yeah, but wait, we have these great tools in the Linux, LXC, but which had a lot of manual configuration that you had to do in a lot of different files. He said, why don't we use that? And why don't we use that concept of what the Solaris zones started and do something like VMs, but then much faster. And on the application level, we'll do isolation. That's what Docker did. And they did it in a user-friendly manner so that it stuck with developers who wanted to do something very fast, very rapidly. They also said, well, we're not just going to do that on Linux, we're also going to do it on Windows, we're going to do it on Mac, we're going to go cross-platform. So this very popular is still the most used container technology. I see someone nodding no. Which one?
Nobody knows.
If you're running newer versions of OpenShift or any of the Cube ones, it all might be.
Yeah, you're right. You'll see that on the next slide, but I would dare say that the developers and students, will still use Docker to create containers and learn the basics of containers. But if you're going to production, I would definitely not advise using this, which is what I'm getting at. So you have a Docker Hub, which gives you a library of container images where you can download your applications from, which are then spawned on your machines. Here you see an example of Docker Hub, let's say. So you see that that's a public website, you can just look for your favorite component there, and you can find an official Docker image typically of that component. You have Redis here, you have Ubuntu, Postgres, whatever you want, whichever type of component you want, you can probably find a Docker container image on Docker Hub. But that doesn't solve our issue. So if you look at this, this is actually a depiction of it should play a video, and it doesn't. No, okay, it doesn't. What you see here, it should animate, is these are microservices that make up Netflix's backend. So you see it there, ELB, that's the Elastic Load Balancer. That's the entry point to Netflix. All the other services are actually backend microservices. If this were to animate, you would see that there's quite a large number of communication between all these microservices. So the key here is, even if you have containers, even if you know that your application can get divided into microservices, the challenge here becomes complexity. How do you manage this? How do you deal with upgrading, with updating? How do you deal with, if something goes wrong, where do you find what's going wrong in this mess, let's say? Parts of this can be solved by knowing what is happening in the cloud-native landscape, by selecting the correct technologies for granting, among others, observability to your application. So, but what is the cloud-native landscape? Well, the definition is that it empowers organizations to build and run scalable applications. I've already mentioned that. Applications that need to scale, you subdivide them into smaller microservices, you put those microservices into containers. How do you do that? You want to do it in modern dynamic environments such as public, private, and hybrid cloud. So not only public cloud, but also your own data center, potentially a mixture of public and your own data center, potentially even multi-cloud offerings. You also want to have loosely coupled systems, because you want to be able to switch out one of the services with a new service, or for instance, you want to try out a new technology, see if it helps you with budgetary constraints or with performance constraints. You want to be able to swap that out. So you want your loosely coupled system to be resilient. It shouldn't crash. It should not have an impact on your running applications if something goes wrong. It should be manageable. That's very important if you have so many running cogwheels, let's say. And it should be observable, because if it's not observable, what are you going to do if something goes wrong? You're going to guess where the error is? No, you want to know exactly what is going wrong. Things like tracing that was shown before, that can give you an indication. Okay, service A is holding up all my requests. Let's have a look at what happened there. You also want robust automation. So CI/CD pipelines, when you develop a new version, that you can push that new version into testing, staging, production. So the main thing also is you want to be able to make frequent changes. This is not dealing with applications that we won't change anything anymore for the next 5 years. Well, don't set this up. It's not needed. Keep it as is on your server. You don't have to change anything. But if you have applications that you say, we lose customers if we don't every 3 months add functionality that they request, then things like this might make a lot of sense. So what exactly does the Cloud Native Computing Foundation bring there? It's basically an organization that gathers projects that are sometimes open source, sometimes closed source, with an aim to advance cloud nativeness, with an aim to advance the knowledge about cloud native technologies. It was founded in 2015. There's now over 800 member industries, which means industrial partners that are paying to be one of the members of the CNCF. And they organize bi-yearly, I even think it's 3 times a year now, because they also do it in Asia. CloudNativeCon, typically alongside the KubeCon conferences. So you have CloudNativeCon focusing on all the cloud native projects, and you have KubeCon focusing on Kubernetes and what is going on there, what is advancing there. They also do other things like certification and training, but that's not the main thing about why we're here. Looking at the Platinum members, which are, you can consider them the biggest sponsors, let's say, all the big names are there. All the cloud vendor big names, Microsoft, Azure, AWS, Google, IBM, and so on, they're all here. Here's some stats. They now have 141 projects, open source projects, which means there's 141 possible options for you to choose from when you're developing a cloud native software solution, which is a lot. Let's not beat around the bush. This is a lot, and it's very complex to choose the right projects, which is part of what drove us to bring this project to you. There's about 180,000 project contributors. These are people that are developing for those projects or that are writing documentation or whatever, but that are actively contributing. And there's about 50,000 members. These are people that are joining in on these conferences, let's say. They are very interesting. So if you're building cloud native applications, these are not very expensive conferences, and they always do. It's not that expensive compared to academic conferences.
Okay.
They are not expensive for us. Like an academic conference is typically. That could be.
Compared to normal industry, they're expensive.
How much do you pay? Do you guys pay?
Well, I don't pay.
That's not so.
But typically, we pay about that.
Yeah. Okay.
And they're not as technical as they claim.
For us, it's about, I think it's 100 euros or something like that.
Yeah. Okay.
But to
enterprise 10 times.
Yeah.
But to give a
cybersecurity conferences are 3,000.
They are
Okay.
different.
Yeah.
So to give an idea, that was the 200 euros.
Okay. Yeah.
just to put it in perspective, even though we get a discount here, when we publish an open access paper, we pay around 2,000 euro just to get the paper published. That was already accepted. And that we did all the work for, but okay. CloudNativeCon, it's in Netherlands in April. Might be of interest. We typically allow some people to join in on that. You've seen this picture. This is actually the most up-to-date one that I've seen today. You can see that it has grown. This is the number of distributions now. So this is basically the number of Kubernetes distributions that exist. Yeah. So there's a lot of different vendors that have a distribution. You will notice OpenShift is in there, Azure is in there with their Kubernetes service, and so on. And these are actually, so notwithstanding the bottom here, these are actually all the open source projects that you can choose from. I'll zoom in on a few just to give you some idea about the mess you're getting in, yeah? But also, I'm not gonna say the mess you're getting in because there are some very, very promising projects in there. And what our aim is in this project is to get you accustomed with, these are the good ones that you need to follow. And these are the ones that you can just leave aside because they will mean nothing to you, yeah? So let's start with container runtime ecosystem. I've already told you Docker. Docker is a container runtime. Yeah? It's more than that, it's tooling and so on, but I'm going to keep it simple. You can already notice that, yeah, but wait, there's not only Docker, there's a lot of competing technologies there. Yeah? And some of them are more focused on security. If you need to run secure workloads, I wouldn't advise you to run that on Docker. I would advise you to look at the trusted container ecosystems, or to look at things like Kata containers, because they're actually micro VMs. So you see that you had Docker, and Docker is known for being not that secure, let's say. You also now have things like micro VMs. So we're dabbling into that VM terrain, but these are VMs that have very fast boot up times, that can do a lot of things, hardware isolation and so on, that allows security to shine. You also have things like sandboxing. Sandboxing technology like gvisor. We've actually shown in research that this is not the best performing technology, but it's still of interest. If you're wondering what sandboxing is, if you ever use the browser, that's sandboxing. There's a sandbox around your browser that prohibits outside parties from running code on your computer, unless you allow them, of course. Unikernels, a bit competing with containers, but I won't go into that. And then you have the quite new WebAssembly, which is very promising and which we're also investigating. You can see WebAssembly as like a micro container. Yeah, so a very, very highly performing container coming from the web sphere that is making its way towards edge deployments. When I said Docker is not the only thing, this is actually how currently we see the container landscape. You have low-level container runtimes that operate at the operating system level. This is where Docker is operating now. You have things like micro VMs that actually place some micro VM around your container and then start your container for security. You have WebAssembly. Again, a kind of extra wrapper around your container, but it boots a lot faster. Well, it's difficult to explain, and I'll just leave it like that. You have sandboxing technology. TEE is trusted execution environment. That's if you want to do things that the resource you're running on, you also don't trust. Yeah? Let's say that you want to do banking stuff, and you want to put that workload in the public cloud, but you want to do it in a confidential manner so that the person hosting that resource cannot look at what you're doing. You'll want to look into trusted execution environment containers. This is also something relatively new. You then have high-level container runtimes where you have to make a choice. You have container D, which is probably the strongest option at the moment. You have CRIO, which is the Red Hat alternative, which is, among others, integrated with OpenShift. And you have libpod that handles with Podman, which was already mentioned here also. And then you have your container management layer. And there you can use Docker. Docker Swarm still exists in some form. I wouldn't advise doing that, but you have Kubernetes. You have things like Nomad, as was mentioned here, and you have things like Podman. All of these, you have to make choices. What are we going to be running in production? What are we going to use as high-level container runtime? That's actually a choice you have to make. And I know there are opinionated Kubernetes distributions that make that choice for you, but you still have to know what is behind the scenes here. Am I making the correct assumption? That was it for container runtime. So orchestration and management, then again, you see a lot of different projects that can be used. I think Kubernetes is the most well-known. Nomad has been mentioned here too, from HashiCorp. A lot of things, a lot of these CNCF ecosystems revolve around Kubernetes. Yeah. What is Kubernetes? I told you, microservice-based applications consisting of 50, 60 to 100 services. But that's not it. That doesn't mean it's running 50, 60, 100 containers. Each of these services has a number of instances being spawned depending on the load that it's getting. So you can have thousands of containers per application. Things like Netflix and Facebook, millions of containers running at all times. You need something to orchestrate that, to manage that for you. And that's what Kubernetes does for you. You can do things like service discovery. You can do things out of the box like load balancing, secret and configuration management, healing. So it's declarative. You specify, I want an application to at all times be up with 3 instances. Kubernetes will continuously loop and continuously look, are there 3 instances? If not, I'll make it 3. Are there 4? No, I'll ditch 1, I'll make it 3, and so on. So that's what Kubernetes can do for you. There's a lot more. We would need 3 hours just to explain all this. It looks a bit like this. For those that know the Kubernetes architecture, these are essentially your workhorses. There's 2 pictured here. Basically means 2 servers that are doing the work, that are running containers. For us in our data center, this can be tens of nodes. I mean, in the public cloud, you can probably have hundreds of nodes on your Kubernetes deployment. But these are the workhorses, and to the left there, that's actually the brain of Kubernetes. So that's where the decisions are being made. That's what is reading your configuration and that is attempting to enact your configuration on that cluster. The main aim of Kubernetes is make sure that the applications that it needs to run are kept up and running, yeah, in the state that you want them to. And you can see your end users are going through a load balancer to get to the different nodes on which that application runs. They typically don't know that Kubernetes is behind it, nor do they need to know that Kubernetes is behind it. They are just care about, is my application reachable? Is it running? Is the performance I'm getting from it okay? So this is Kubernetes. Again, I'm going quite fast, but it's just to show you that this landscape is complex. And what we aim to do in the next 3 years is actually deep dive into each one of these subdomains and look at interesting choices there. So this is, for instance, the database landscape. Vitesse was already mentioned as that system that allowed YouTube to scale. Yeah? But it's purely aimed at, I think it's MySQL and MariaDB, which yeah, Luca mentioned it, which it can aim for. You have here also a key value store, TIKV, titanium key value that is, which is also a graduated project, which in turn translates to an actual new SQL data store if you put another layer on top of it. Now, it's very difficult to get an organized idea about what is of interest, and that's what we're aiming to do. So in terms of relational data stores, graph stores, time series data stores, document stores, key value stores, there are good options here which are fully compatible with Kubernetes, so which you can use alongside Kubernetes, which can be installed on Kubernetes, which can be scaled on Kubernetes. Well, we see that, I hear you say don't, but we do see that there are data stores which are perfectly compatible with Kubernetes.
You don't care about your data.
Why would you say?
Because containers and storage. Yeah. Not a solved problem.
Containers are stateless, so how are you putting data in them?
Yeah, but okay. What you're doing is actually you're just installing your data store in your Kubernetes cluster, and you're having an operator which manages your data store. This doesn't mean that you're running this as a container next to your other containers.
Yeah, because where's your data?
In your data store.
Which is containerized.
Which is containerized. So where is your actual data?
Well, it depends. You can either use an external data store like a cluster, which connects to, if you really want it, NFS to your Kubernetes cluster, and use those as persistent storage. Or you use an operator like Rook, which can actually turn like the.
But even that's running inside of you.
Yeah.
That's not a bad option, right?
And so you.
But that's not the.
If you care about your data, you can do that.
Why would you not run Ceph?
Look at the number of kernel plans over the years with Docker and containers.
With Docker, but you shouldn't run Docker in production, right?
It's not mature.
Even that, how do you guarantee that when the fault comes up, the data will be there? Unless you put that in an external data store. Again, you're not solving a problem here. The data needs to be somewhere. If you're going to put that into your pod, that's wrong, because you do not know where the pod will come up. It might come up in an X data center. And where's your data then?
Well,
how does it get access to that data?
This is managed by Rook.
Yeah, which is actually in 2 slides further. So you have your database, which allows you to query your data and to store your data. Your database stores its data on whatever you choose underneath, which is then your storage layer, which in our view, we still have NFS, but we would like to ditch it because we'd really like something like Longhorn or Rook underneath, which deals with Ceph. For us, I mean,
Ceph is external. Yes, the Ceph is inside your ecosystem.
But why would you need Rook then if your Ceph is external?
Yeah.
Okay, it's a strange thing because according to our
industry is trying to believe what they're trying to push. But
yeah,
all these introductions so far are failing.
Yeah,
Each time we try again, we both like.
We've been running Rook for quite a long time, and
What workloads?
it seems to.
If you look at the CNCF I think it's a survey they sent to companies that are struggling with data. The #1 solution there is Rook plus Ceph, and that's I think 18%, and that was a survey that was taken last year.
I don't know if on prediction and stuff, but look at AWS. Are you running your container storage inside the container, or are you actually using external RDS? Are you
Actually,
using external?
We also buy still.
Yeah. But then, if you look at the same survey, where with companies that have very high demanding data applications, they don't choose Amazon. They also don't choose Azure. That's like the 5th choice or so. Okay. If you
have storage needs,
what would you recommend then? Yeah. Yeah.
Also, your storage cost is going to be a problem.
Yeah. Yeah, we do things differently than a bit. Okay.
For running book inside, and it's very well horizontal.
And that's in your own data center, or in your own data center, or somewhere else? Yeah. Yeah, but that's how we also run it. Yeah. Yeah. We also have a very good experience with Minio. That has also been running very well for the past, I think, 3-4 years or so. Okay. Not to divert. So gone are the days where you just have FTP, which I still see with some companies, or pure Samba or NFS. You now have options. You can go for file-based storage, block-based storage if you really need, or object storage, things like S3 buckets, but you can have that in open source variants also. So there's a lot of these technologies that work quite well with Kubernetes, that can provide you with operators that can be installed quite nicely on Kubernetes. Looking at monitoring, and we've also dived into that with some cases. Yeah.
The previous slide. So cloud-native storage, and nobody's talking here about data protection. So I see there custom, for example, custom and Valero. I think it's more software that is specialized in backup and restore of so data protection of containerized workloads, because it's special. To take consistent backups. So you see it as storage, but in fact it is data protection.
Yeah, I think there's 2 of these, Ketchup and Valero, which are actually backup solutions, but they use storage to store that backup. So they just catalog it as under the storage thing. But it's very different. These are 2 very different solutions from, for instance, Longhorn or Ceph.
Yeah, because when you make an architecture of containerized workloads, it has to be resilient, it has to be secure, it has to be observable.
Yeah.
But it also has to be data protected. So I think it is another use case that is important, because it is different with monolithic workloads.
Yeah, you're totally right. Yeah, what you have with some of the technologies here is that they don't offer backup functionality, while some others, like Rook, they offer backup functionality, which you then don't need Ketchup or Valero.
Portworx also. Portworx is, you can create persistent storage. Yeah, it's open source, but it is now pure storage proprietary as well. So Portworx, you can build persistent storage, but you also have a software behind to replicate the data and to backup and restore the data. So it is storage, but it is also data protection. Yeah.
I typically only know the pure white blocks because those are open source. The gray ones are actually not open source. Okay, but there's a lot to dive into if you go into the storage landscape. I think I once did a study on the open source versions only, and I came up with an 80-page document, just cataloging their strengths and drawbacks.
Because I am really surprised that when I hear you talking about production storage,
and more we are talking about software-defined storage. So the software set, yeah, and set, but there is also more and more. It's the software set. It's also monolithic. There's a monolithic version. There is a containerized version, and more the software is really containerized now. So what you are saying is that, yeah, it is not the right, or is it just for databases? And because you have file systems, you have object storage, you have so different kind of storage. So none of them are really running fine in containerized, or it is not production grade. And that's what we are saying.
Most of the storage things we run are not running containers. They're running bare metal and actively talking to local storage. And they're distributed and they're exposed and containers consumed, but they're not running in containers.
There's not much of a difference compared in like how the actual specifics work. If you run them in Kubernetes, they're also talking to local storage directly without anything in between.
If your CSI,
It's only the compute part that's running in the container. The actual file system is just a mount from the local file system of the worker.
That mount on kernel level is called.
I think it depends a lot on which
Depends on
which
And
which year you're talking about. Like if you're looking at 5-10 years ago, yes.
Did stress tests on it? It's about 18 months ago. But before that, it was every time we run a test service, then so kernel time and starting to have more started actually before that.
okay, I think we just have different experiences then with that. But it might be interesting to have a look at what's going wrong there.
We looked into that and I want to revalue it up. Part of the experience we have was containers and storage.
Moving to monitoring, Prometheus has been mentioned already, which is a very good monitoring solution. I won't dive into it, but you can see that also there. There's a lot of different open source solutions which deal with parts of this observability issue. There's plenty of other domains, so I've only touched a few now, zoomed in on a few, and only gave bare minimum of explanation. You have things like coordination, service discovery, API gateways is also quite a large one, service meshing, and so on, cloud native networking, and so on. But our aim is really to dive into those and provide you with insights in terms of what is useful for us, depending, of course, on your own use case. So to conclude, we're trying to get you to see the forest again through the trees, because as you noticed from that CNCF landscape picture, the overview, it's just too big to make decisions anymore without being an expert on some of these technologies, or without having a very broad overview over different use cases in terms of what are interesting choices, what choices should be left. We think the CNCF offers some very good technological choices, but there's also a lot of choices there that are not good. Let me put it like that. That are, for instance, if you look at the storage side of things, there's, I think, 1/5 of the projects that are purely aimed at the Chinese market, that are purely aimed at the Alibaba ecosystem, which will not be documented well, which do not operate well on European or American cloud systems. So the projects will try to lift the veil of select areas of these cloud nativeness, and will also try to get a sandbox up and running that allows you to experiment with these, to see how does it work, what are the strengths, what are the benefits of it. This is the team. There's one person not here, Tom. He was following a little while back online, so hi, Tom. But you'll get to know him over the next sessions. Okay, any questions? Okay, thank you very much.